So let's prove the inverse function theorem now. So the proof. Okay. Yeah. So what we do is that, so I'll first suggest, please go back in the previous lecture and see the statement of the inverse function theorem clearly. And there was a lot of motivation given, a lot of idea given, that why we essentially want to talk about the inverse function theorem, and that will help you understand the logic better. Okay. So I'll obviously suggest you please go and have a view at the inverse function theorem, statement of the inverse function theorem, and the idea behind the inverse function theorem first. Fine. Okay, so let's prove it. So we will actually try and use the inverse function theorem. And yeah, so let f be a map from a f e to Rn. So let this be the function given by, so what we do is that we construct a function, we takes any n tuples and it maps it in this way. So it keeps the first n of the elements as it is, and the nth element it takes in like this. If you recall, then f was a real valued function on E, and f was continuously differentiable. Now since f is continuously differentiable, this implies that f, capital F, is also continuously differentiable. And what is f of y? So f of y would be given as the first n coordinates of y and the image of y under f. But again, recall the statement of the implicit function theorem. There we had stated that f at y is 0, right? So this implies that this is of this form, 0. Fine. Now what is the Jacobian of f at y? So we know this by formula is just this. Fine, we take all of these as columns. So del f by del xn at y, and take its transpose as column. So now you can clearly observe that when we are partially differentiating it with respect to x1, so the derivative of the first component, it will come out to be 1 because it is just x1, and the nth component will be the derivative, partial derivative of f with respect to x1 at y, and all the other components are 0. And in the next case we have 1 here, and all the other components are 0 with the, so let me draw it a bit bigger. Fine. So the first component is just x1, so its derivative with respect to x1 is just 0. The other components are all 0, and here I have del f by del x1 at y. Similarly, in the second case we have the first L component to be 0 under derivative. The second component will be 1 because the derivative of x2 with respect to x2 is just 1. Again, all the other components are 0, and the last component is just the derivative of f with respect to x2 at y. And this continues till the second last component being all the elements being 0, with the n minus 1 component being 1, and the last component being del f by del x n minus 1 at y, and the final component, in which final column in which we will have all the elements to be 0, and the last will be del f by del xn at y, right? Fine. Now since we had assumed that the partial derivatives at y are all non-zero, sorry, we had assumed that del f by del xn to be non-zero, sorry, yeah, we require this only, yeah. So this immediately implies that the derivative or the Jacobian is invertible. Okay, that is, the determinant of the Jacobian at y is non-zero, which implies that this Jacobian matrix at y is invertible. Fine, this is invertible. Now once this is invertible, then what we can do is that we can go for the inverse function theorem immediately. In fact, we can structurize out the inverse which you can verify on your own. It is just, so all the elements remain as it is. I have 0 1 so on till 0 here. Here I have 0 0 till 1 here, and here all the elements are 0, and the last element being 1 over so this is 1 over del f by del xn at y, and all these elements are of this form. So it is of the form minus del f by del x1 at y divided by del f by del xn at y, and similarly this component will also come out to be minus del f by del x2 at y divided by del f by del xn at y. Fine. Now since this derivative this derivative is invertible at y, so we can apply the inverse function theorem. Therefore, by the inverse function theorem, there exists an open set V in E. Now the derivative is invertible at y, so containing y, and correspondingly, and an open set W in Rn containing the image of y under capital F, because capital F is the function which we are dealing with, and capital F is basically equal to this 0, such that F is bijective from V to W, and F inverse is differentiable at f of y, which is equals to y1 till yn minus 1 and 0. Fine. So this is just the application of the inverse function theorem. Fine. Okay. Now for any x, for any suitable x, that is keeping in mind the domain and the codomain, we write f inverse x as coordinates. So I write it as h1x till hnx, because we are choosing values out from Rn, where or rather, yeah, so now x comes from W, right, for x in W. Fine. Now since f applied to f inverse x, this is just x, this implies that hjx1 till xn, this should be xj, right, for all was less than equals to j less than equals to n minus 1, and x belongs to W, and the function f, this is like this, equal to x. Fine. Fine. Yeah, just go through the statements and you will get to know what's all happening. You need to write it along with me, and then analyzing each step you will get to understand what's happening. Fine. And it is quite easy to observe that since f inverse is invertible, each hn is invertible. Sorry, not invertible, differentiable. Extremely sorry. Since fn is differentiable, hn is differentiable. Differentiable at this coordinate, of course, y, f at y, n minus 1, right? Yeah. So now all we require is to have the open set U, nothing else. So we just construct out U. So let U be the collection of all the n minus 1 tuples in Rn minus 1, such that this element 0 is in W. Now E is clearly open, right? Therefore U is open and contains the coordinate y1 till yn minus 1, 0. right, because it satisfies this condition. Fine. So now all it we require is to define G, nothing else, right? So define G to be a function from U to R by just taking these n minus 1 tuples and mapping it to Hn. Fine. Then G is clearly differentiable at Hn is differentiable. We just saw that Hn is differentiable at the coordinates y1 till yn minus 1 comma 0, because f inverse is differentiable. So G is differentiable at, so Hn was differentiable at y1 till yn minus 1 comma 0. So G is differentiable at the coordinate y1 till yn minus 1. Fine. Yeah. So now we are good to go. So so we have the function in hand, we have the required open sets in hand. So all we need to show is that the level curve is exactly equal to the graph under G, right? That's all we need to show in terms of these open sets U and W, right? Nothing else. U and V, sorry, that's all required. So now to show that the level curve such that f is mapped to 0 is exactly equal to the graph. Fine. Sorry. Fine. Okay, such that each of these elements comes from U. Fine. Okay. Now how can we actually do this? It's actually a very simple argument. Just choose a value from the first set. Okay. So let us choose a value from the level curve. So let x1 till xn be in V such that the image of it under small f is 0. What does this immediately imply? This implies that f applied to this is x1 till xn comma 0, sorry, x minus 1 comma 0, right? This was how f, capital F, was structured or defined, and this is in W, right? Once this is in W, this implies that this tuple xn minus 1 is in U. This implies that applying f inverse x1 and x1 till xn, this is equals to the inverse image of x1 till xn minus 1 comma 0. Fine. Fine. But once we have this implies that xn is the image under Hn of this element, this vector, but this is exactly G, right? Therefore we have a one-sided inclusion. Therefore, so I am not writing it anymore, I am just leveling it here. So what we prove is that this is contained here. Fine. And the other inequality is proved by exactly reversing the argument. The other inclusion is proved by simply reversing the argument. And we are done, right? Yeah. So we have successfully proved that the level curve admits a function whose graph is that level curve, and now all we need to show is that the differentiability of G and the structure of the derivative, right? Now what we have is that, see, this is 0, right? By the way we structured it out, this is 0 and this is 0 for all comes from U. We have already have in hand that G is differentiable. and f is differentiable. Where is it differentiable? F is differentiable at y1 till yn minus 1, g at y1 till g yn minus 1. Fine, which is exactly equal to y. Fine. Therefore, the chain rule, which we can immediately see being applied from here, if I apply it to this structure, we can immediately see that del f by del xj at y plus del f by del xn at y times del g by del xj, I guess it will be, yeah, so del f by del xj at y plus del f by del xn at y times del g by del xj at I should get it here, yeah, fine, it will be the first n minus 1 tuple, yeah, this should be 0, and we have, okay. Actually, this is a small remark, and it's actually something which you might study if you take up a course in advanced topology. This is exactly not the definition, but it is somewhat the idea. That is, the sets which look like graphs of continuous functions are called manifolds. Manifolds have a slightly stronger meaning. So manifolds are basically, I guess it's a Hausdorff second countable local Euclidean space, or in other words, manifolds are basically generalized surfaces. So these are just surfaces, they are spaces which are locally diffeomorphic to open sets in Rn. Okay. Or rather, you can, for now you can think of it to be homeomorphic to open sets in Rn, or in simple words, that if I choose a very small region from this surface around some point, then that resembles an open set in Rn. In that case, we say that talk about a manifold of n dimensions. So that's quite a bit advanced topic in topology, what we typically call differential topology, and there we deal with these generalized surfaces or manifolds. Somewhat the introductory notions of manifolds is what we are dealing with in this series. Okay, all of these things are sort of the introductions to manifolds. We study the spaces Rn completely, and once we move on to manifolds, we will see that every property of manifolds are just the generalization of these properties itself, and the proof of those properties exactly come from these properties we studying in Rn to Rm, because we can just work out through these diffeomorphisms, and the diffeomorphisms are basically, you can somewhat think it to be smooth functions. Okay, these are smooths. You can talk about derivatives, you can talk about infinitely many derivatives, sort of things like that. We do not want to go deeper into those things, but these are the things which you will be eventually requiring if you take up a course in manifold in some point of your career. Fine. Okay, yeah. A quick example should be considered as to be this surface. Is it? So one example we had seen in the previous lecture itself, where we were discussing about the idea, but that was a very simple example. We had discussed that in R2. Here we discuss an example in R3. So this is a level curve given to us. Okay, level curve in terms of, so the function fxyz, so it takes values from R3 and it's a real valued function which can be easily observed out from here, like yeah, so this is basically f. Fine, this is your f, right? Rather we take it in this way. So this is the, yeah, this is 1, so we can equate it to 0. Yeah, this is the level curve at 0. Fine, this is the level curve at 0, because since we are talking about level curves at 0, so I need to take in this function like this, right? When we were discussing about the idea, we had talked about the level curves at any constant, but then equivalently we can talk about the level curves at 0 by just taking the constant inside the function. Fine. This can be easily seen that f is continuously differentiable. f is continuously differentiable, and what is the derivative at z, so it's just x plus y, right? Fine, I guess it should be better, yeah, it's y plus x, but still it's x plus y. Fine, therefore, so I need this derivative to be non-zero in order to talk about the implicit function theorem. Therefore, for all x naught, y naught, z naught in S such that y naught plus x naught is non-zero, there exists a function say g such that xy, g at xy such that this tuple xy comes from some open set U which contains x naught, y naught, containing x naught, y naught, is the corresponding graph, and g is differentiable at x naught, y naught, and moreover we have that the derivative of g in terms of x at x naught, y naught is just y naught by z naught, y naught plus z naught, y naught plus x naught, using the formula we had given for the derivative of g, and similarly the derivative in the y direction is just minus x naught plus z naught 1 y naught plus x naught. Fine, right, okay, so yeah, so we are good to go. So let this be the end of this lecture. In the next lecture I'm a bit confused about what to talk about, but I have an idea to talk about the Clairaut's theorem in the next lecture, where we talk about the mixed partial derivatives, and if we do not talk about that in the next lecture, we will come up with some other topic in several variable calculus. So meet you guys in the next lecture.